visible, then please stop me in between my speech, okay, and just tell me. So, am I audible?
Yes, sir.
Okay, thank you for the response. So, good morning again. Uh, I hope all of you are doing great. Your examinations are near at hand. The lab exam will be held on tomorrow for this vibration. I think all of you are aware about that. At 2:45 sharply, I will be uploading the question paper. Okay, uh, in the vibration lab portal in the Google Classroom, not in theory portal. In the Google, vibration lab portal, I will be uploading, and all of you need to answer, okay, the elaborative answer, because there may be some 1 mark 2 mark question, okay. So basically the total marks will be 20 marks and the duration will be 1 hour duration, and there will be 1 marks or 2 marks questions, okay. So you need to give the elaborative solutions, okay. Don't write only the answer. If it is a fill in the blanks type question, then only you need to write the answer. But for this conceptual, okay, or some formula based problem, so you need to write the formula and the result as well with unit, okay, proper unit. So now let's start our last module, that is control system engineering, okay. So I will be sharing my screen. So I think the screen is a little bit fainted, okay. I am not using actually the magic color from the cam scanner, because when I used, so some of the words were actually not that much visible. Now also it is not that much visible, but it will be clear to you when I will make you understand, okay. So this part is not the tough part, very simple part. So I will tell you one by one, okay. So basically, what is a control system? Okay, so actually it is a combination of components connected to perform a required, required, you can say, task. Okay, so that is called as a control system. Means whenever we will say any control system in any kind of equipment, that means we can control that device, or the device can control itself, and it will adjust with the conditions whatever it is given. Just wait, I think someone wants to join. Okay, so for some devices actually it is very much essential. Just wait, okay, I have a call. I have to attend it. Okay, thank you. Um, so it is a combination of actually components connected to perform a required action. Okay, so these control systems basically they are mainly classified as manual and automatic. Okay, so in our general language, so we'll classify them into two categories. So basically you can see some of the examples that whenever a fan, normal fan, we need to actually, if we need to decrease, or if we need to increase the effect of the fan, okay, effect of the fan, so what we will do, we will be actually rotating, we'll be rotating the regulator. Okay, so there will be 5 steps. So in 2 steps you will get less power, okay. In a fifth step you will get more effect, okay, from the fan. So we need to do it manually, isn't it? But in our air conditioning system, so though we put the temperature manually, but what the system is actually doing, so the system will control the temperature. Suppose you want a 16-degree temperature, okay, inside a room. So what the system will do, the system will try to measure, okay, through some sensors or through the help of some transducers, okay, and it will automatically maintain 16 degrees centigrade, okay, inside the room. by doing some internal processes, okay, that is RAC processes, refrigeration air conditioning processes, it will do the thing. So automatically the system adjusts with the surrounding, so that is an automatic system, okay. So in manual system, so actually what it is happening, the system, it is not adjusting with the surroundings. When you are rotating the switch, okay, or rotating the regulator, suppose in the second step, okay, so in the second number, so what you are getting, whatever be the temperature, so you will be getting the same rotation, same RPM you will get, okay. So the desired effect you may not get, okay. So in winter you may get it in one, in hotter days, okay, you may get in five, okay, means that regulator, normal fan regulator. So those systems are basically manual and these automatic systems, okay. So here, if we classify this control system engineering or this control systems, so basically there are two categories, okay. One is the open loop control system, second one is the closed loop control system. So here in this PDF file, so you will be able to see the open loop classification of control system. First one is the open loop control system, second one is the closed loop control system. This open loop control system is nothing but the modification of this manual control system, okay. And this closed loop control system is nothing but this automatic control system, okay. So here some examples are written by the side of this definition of this control system, okay. So what is an actually open loop control system? So in electrical engineering, so the open loop control system is one which cannot adjust itself to the changes, okay. So as I have told you, cited the example of the normal fan, okay. So that is also an example of this open loop control system. So whatever input you will be giving to the system, the controller will be converting that system, okay, to the output. Controller will be converting the signal to the output, okay. So if you are just giving here 20 degrees centigrade, the controller will convert that 20 degrees centigrade into analog signal. The digital signal will be converted to analog signal, and it will try to give 20 degrees centigrade. But here it is not mandatory that you will get 20 degrees centigrade or not. Okay, in winter you may get 18 degrees centigrade, or in hotter days you may get 25 degrees centigrade. Okay, so this temperature, it does not actually adjust. Okay, this system does not adjust with the input. So in the input, you are given 20 degrees centigrade, but at the output, the system will show 20 degrees centigrade, but if you measure it, it may be 25 degrees centigrade, or in winter days, it may be 18 degrees centigrade. Okay, so here this RT in electrical language, engineering language, this small r of t is called as the input signal. Okay, as because they are a function of time, so this is input signal R of T. This UT is the control signal. Okay, control signal. So this controller will be converting the input signal to this output signal. Okay, this controlling signal, and it will be converted to the output signal. So how these input signals are given? So digitally we can give, okay, manually we can give with some other systems. Okay, this controller will convert some those digital signals to analog signal. Okay, and again it will run the system. Okay, it will give the output. So CT is the output signal, QT is the controller signal or the actuating signal, and ROT is the input signal. Okay, so you should remember all these terms. So if I will be using all these three terms later part also. So we will be taking the example of the old days air conditioner. Okay, so in old days air conditioner, actually the conditions were fitted with the regulator. So with the help of the normal fan also, you can take that example, same example. Okay, so with the help of this regulator, the input were fitted. The controller will convert those input signals. Okay,
Not audible, sir.
not audible. Okay, just wait. Okay, I will be joining. Okay, now I think I am audible.
Yes, sir.
Okay, okay. So yes, so these old days these air conditioners, okay, or you can take the example of your this one water tank, filling of the water tank, okay, in our household. Actually this is the household example. So when you are filling up the water tank, okay, so actually you are not seeing the water level, okay. One person should be there at the water tank, near the water tank, and when you are switching on the switch, okay, motor, then another person should be there, okay, or you need to adjust in between, okay. So when the water level will be filled up, so there is no output, means feedback signal, that whether it is filled up or not, okay. So sometimes what happens, our water tanks get filled up and it actually splits, isn't it? So the water spills out, isn't it? So this happens because that is a manual system, okay, that is a open loop system. So output is open, okay, output is not giving any signal to the input whether it is already achieved or not, okay. But what happens, so nowadays these water tanks, okay, are filled with the help of these motors only, but with the help of some sensors and transducer or limit switches. Actually what are the outputs, the water tank, it is achieved, it is again giving the signals back to the controller, okay, or back to the comparator. So comparator will actually compare, okay, the signal. So whatever be the signal it was given, actually that signal is at the output, it is there at the output or not, okay. So suppose you have given 200 liters, okay, so you want to fill up 200 liters of water. So if it is 200 liters or 250, so it will again give the signal back to the input, okay. So then with the help of the sensors, transducer or limit switches, we can limit the water tank, filling up the water tank, and we can fill it, okay, without wasting the water. So that is the example of the automatic system, that is closed loop control system, okay. So here by the normal or manual filling up of water is an example of this one, open loop control system, okay. So here in open loop there will be input signal, but the controller will be converting the input signal or giving the input signal to the air conditioning system with the actuating signal, okay. So RT will be converted to UT. This UT will be giving to the main system, okay, the processing system, and this processing system will be converting the digital signals or whatever the signals to the analog system signals or to a understandable language, and then it will be converting into output, okay. So simply this will be a linear system, you can say this is a linear system in open loop control system, okay. But a closed loop control system, so there is a comparator, okay. So when you are giving some input, so the comparator will what it will do, the comparator will actually sense, okay, the sense the input whatever it is given. Suppose you are giving 20, so it will sense whether it is exactly 20 or not, okay. So there will be sensors, limiting switches or transducers depending on the systems. The comparator will be actually uh, calculating the error, okay. Suppose if it is 20, but here it is sensing that though it is given as 20, it is 18, so 2 units error it is there, okay. So again it will be giving the signals to the controller. So controller with a error signal of E of t, it will be actuating the signal to the system or plant. Here plant means the system, okay. So if it is a refrigeration system, then the processing system will be the plant, okay. So where evaporator, your heat exchangers, all those of processing devices will be there, okay. So U of t is the actuating signal, okay. And it will give the output, okay. So when you were giving an input of 20, let's say 20 degrees centigrade, and with an error signal of 2 degrees centigrade, so it will be producing an output of what, 18 degrees centigrade. So what it will give, because it is having a feedback loop, so it will again give 2 degree, okay, 2 degree centigrade signal, because the feedback loop, in the feedback loop there will be sensors, transducer, okay, and limit switches, all those things will be there, which will be giving the feedback
feedback signal back to the comparator. Okay, so here again comparator what it will do, it will adjust. Okay, it will adjust the temperature of the room with the input signal, because here you are giving 18 degree, okay, but your temperature is 20 degrees, so 2 degree again it will give back to the system. Okay, and it will adjust, and finally after one cycle, two cycle, okay, whatever it is required, so it will depend on the manufacturer, so it will giving the 20 degree centigrade at the output finally. Okay, so it needs some time. That is why all those signals are the functions of time. Okay, R of t, E of t is the error signal, M of t or U of t is the control signal, or this one exciting signal, C of t is the output signal, and B of t is the feedback signal. Okay, so I think my screen is visible to everyone. So here this thing is written. So this is a schematic drawing, okay, or this is configuration for a closed loop control system. Okay, this is manual as well as automatic. This can be manual as well as automatic, but there should be a feedback loop. Okay, you cannot write this is a manual system, you have to write that this is a manual system with a feedback loop. Understood? So here this is the linear system for an open loop control system. Very a simple drawing, okay, or schematic drawing or representation for an open loop control system. And here this is the schematic representation of this closed loop control system. Okay, so if you are asked the examples of open loop and closed loop, so you can give the examples of filling up the water tank, or the old is regulate this one air conditioners. Okay, and for this closed loop control system you can give the examples of your this one present is air conditioning system. Okay, motor driving. Okay, so driving a motor car, it is also basically human based closed loop control system. Okay, but we actually generally need to give the examples of mechanical systems. Okay, so that is why you can give the, if it is asked, you can give the examples of air conditioning system. Okay, modern days air conditioning system for closed loop control system. So here in this part, so this closed loop control system example, it is written by taking this one air conditioning system. So here you can see this is the RT, that is the reference temperature or input temperature or input signal. This is comparator. Okay, so comparator will be there, which will sense the temperature, output temperature with respect to the input temperature. Okay, because of this feedback signal. Okay, then the controller will be there. So the in the controller this E of t will be fed, then U of t processing signal or exciting signal will be done by this amplifier. Okay, earlier there was system amplifier plus air conditioning system. So U of t will be fed to the amplifier, so it will convert this digital signal into analog signal, and finally you will get the CT. So here it is not distinct, so you just take a pen and paper and you write it here that this is CT output. Okay, so one arrow mark and one line will be here. So this is C of t output signal. So the output signal, again it will be measured by these temperature sensors. Okay, so this will be a feedback loop. If your desired temperature is not the exact temperature what actually you have given as reference temperature, so again it will give back to the feedback loop. Okay, so it will give the feedback by this feedback loop. Okay, B of t signal will be given to the comparator, so it will again sense or compare this temperature, okay, output temperature to the input temperature, and if there is some error, again it will be sending back to the controller. Okay, and finally you will get the desired temperature after some time. Okay, so all these things it is written here. So just like driving the car, that is also a example of closed loop control system, but that is not a mechanical example of closed loop control system. Okay, so what happens when a person, maybe some of you can also drive a car. So what happens suddenly when there will be an obstacle, or when there will be okay, some this one speed breaker, or okay, some animal it is there. So sometimes unknowingly, okay, by your subconscious mind you apply the brake, isn't it? So why actually it is happening? So when actually you are giving the accelerator you are giving your car a velocity or speed of, let's say, 60 kilometer per hour. Okay, so your feed output is what? Your car is actually driving with an velocity or with an speed of 60 kilometer per hour, instantaneous speed 60 kilometer per hour. But suddenly when there is an animal, when there is an obstacle, speed breaker, so you apply the brake. Okay, suddenly it happens. So why it is happening? Because there is a feedback loop. Okay, your subconscious mind is the feedback part through which your mind is actually getting the signals. Okay, the feedback signals, and without knowing anything, okay, without unknowingly you are actually just pressing the brake, okay, or reducing your accelerator, isn't it? So that is your feedback loop. Okay, so eyes for road and mirror view, and ears for hearing this one alarms, okay, or whatever it is. So this is a human actually mechanism of this closed loop control system. Okay, so actually to understand the thing, actually I have cited this example, but this will not be applicable in our mechanical field. Okay, so I think up to this much you are getting the things for this control system engineering. I want to take some feedback. Parimal?
Yes, sir. Yes, sir.
Okay, Manas, thank you. Okay, so here it is the comparison. Actually I wrote it very fast. Okay, that is why I don't know whether it is understandable for you or not. It is a little bit distinct problem. I think you won't get any problem to understand. Okay, so here it is comparison of open loop and closed loop control system. Okay, so you can see there are two columns, so where I have actually tabulated this difference. So open loop system, it is actually not preferred because of inaccuracy and unreliability. I have told you that in manual control system you cannot predict actually what will be the output. Okay, so when you are giving 20 degrees centigrade, so you may not get 20 degrees centigrade. In winter you may get 18 degrees centigrade, and in summer you may get 25 degrees centigrade. Okay, that is why closed loop systems are more accurate. Okay, they are very much accurate actually. So a closed loop control system is more accurate because the error between the reference signal and the output is continuously measured through the feedback signal with the help of this comparator. Okay, so here in the second point, system is more economical and simple to construct. It is very simple linear system. So system is very expensive because sensors, transducers, all those things, electrical electronics components are used. So that is why the system is very much expensive. Okay, so here, so the system is generally stable. So why it is stable? It will be stable because it is having less components. Okay, so whatever signals you are giving directly linearly, they are converting to the output signals. So it is very stable. But here the system is not stable because feedback loop is there. So in 2 minutes you are getting 18 degree, and in 5 minutes you are getting 20 degree. Okay, so the system will try to adjust, okay, with the surroundings, isn't it? So that is why this is not stable system. So sometimes this actually here there is a disadvantage of this closed loop control system, because sometimes they will lead to oscillate, okay, because of their instability. So that is one actually disadvantage of this closed loop control system. Okay, here in open loop control system, the stability of the system is affected as it does not adapt to variation to the environmental condition or external disturbances. Okay, so stability sometimes it may affect, here it is written, but here stability of the dynamic system, it is not affected, but in dynamic condition, okay, so the stability it is not affected. Okay, so overall the system is stable for this open loop control system, but for this closed loop control system, the stability of the system is not affected due to the reduced effect of non-linearities and distortions. Okay, so if some distortions means what? Non-linearity. Okay, non-linearity will happen, the system will try to adjust itself because there are some electronic components. Okay, and again it will be giving the signals back to the comparator will be giving the signals back to the controller will be giving the signals to the system, okay, or the processing unit, then again it will adjust. Okay, so if you just understand that means in overall condition the stability of the system, it is not that much affected due to the non-linearities. Okay, so it is on the basis of non-linearities and distortion. So here it is on the basis of this non-linearities and distortion for this stability. Okay, this is not that overall stability, this is stability against these non-linearities and distortions. Okay, so yes, so till now, whatever actually system we have studied under underdamping condition or in force vibration in damping condition, so we have used some of the basic principles of mechanics. Okay, so those are actually some D'Alembert's principle or Newton's second law of motion. Okay, so basically we have used those kind of equations, okay, of motions to analyze the system. Okay, so manually we have analyzed each and every system under different conditions. Okay, but mathematically if we need to analyze a system, so we need a parameter. So that parameter to represent a system mathematically, okay, and to analyze the system this one mathematically, so we need a parameter which is called as the transfer function. Okay, so before knowing the definition of this one transfer function, so first we will see the features and advantages of these transfer functions in control system engineering. So what actually transfer function does? So using transfer function, so mathematical models can be obtained and analyzed. Okay, uh, actually what is a mathematical modeling, if I will ask you? So basically the process of actually obtaining the mathematical description of a system. Okay, it may be the differential equation of motion, okay, whatever it is, by applying any kind of laws, just like your Kirchhoff's law for electrical system or Newton's laws of motions for mechanical system. So that kind of mathematical description, actually it is called as the mathematical modeling. Okay, so here these transfer functions will help in actually getting the mathematical models, okay, and the analysis of the system. So output or response can be obtained for any kind of input, so with the help of this transfer function, and the stability analysis can be performed. So the uses of Laplace transform, so we will be using some Laplace transform. I think all of you have studied a Laplace transformation. Okay, so here also there are some of the applications of Laplace transform. I will show you later in this class. So the uses of Laplace transforms converts the complex time domain equations to simple algebraic equations. Okay, so with the help of this transfer function, we can convert those time domain complex equations to simple equations, algebraic equations. Okay, so analysis of a system is simplified due to the use of S domain variable, because if we apply Laplace transform, so we need to apply this, we need to use this S domain variable. Okay, so in Laplace transform we use S domain variables in mathematics, so in the equations, rather than using time domain variable. Okay, so here all the signals you can see in open loop system or closed loop system, so all the signals are actually time dependent. But in Laplace transform, when we will be analyzing any system or when we will be describing any system, we will be using S domain variables. Okay, so those variables will not depend on time, so those variables will give the output with respect to the input, those variables will give the feedback signal with respect to the output. Okay, the anything related to the system can be easily found out with the help of this transfer function. Okay, so that is why it is very much important to study this transfer function under this control system engineering. So what is the definition? The transfer function of a linear time invariant differential equation system is given by the ratio of the Laplace transform of the output variable to the Laplace transform of the input variable, okay, or the driving functions, because these input variables are what? These are the driving functions. When you are giving some input temperature to a refrigerator or to a air conditioning, so that is a driving function, okay, driving signals. But this ratio out to the output signals to the input signals when all the initial conditions are 0. Then only we will be calling it as a transfer function, or this is actually gain. Okay, gain function. Okay, for open loop system it is generally denoted by GS, or you can say output gain, okay, or overall gain of the system. So for this open loop system it will be denoted by G of S. Okay, so G of S will be equals to Laplace transform of the output signal. C of T is the output signal to the Laplace transform of this input signal. This C of T can be represented by capital C of S, because all the time dependent variables will be converted to S domain variables. Okay, so in the features of transfer function I have told you that in Laplace transform, so we will be using the variables under this S domain. Okay, and here it is the input signal or the reference signal with respect to S domain. Okay, because we will be using Laplace transform to analyze the or configure mathematical model for any kind of system, damped system, undamped system, force vibration system. So we will be using this domain only, C of S, R of S. Okay, so when zero initial condition, at zero initial condition, so this is must. Okay, so when you are defining this transfer function, so you need to write this one, otherwise it will be incorrect. So this is the ratio of Laplace transform of output variable to the Laplace transform of input variable when all initial conditions are 0. Okay, and basically this transfer function is represented by T of S. Here you need to write actually T, capital T in bracket S, that is transfer function. Why I am writing here G of S? Because for open loop control system, okay, so this T of S is equals to G of S. This is called as the overall path gain, G of S. Okay, and for open loop system this is only the transfer function. Understood? So here this point also you can remember. So nonlinear and time variant system does not have any transfer function. Okay, because they do not obey the principle of superposition and homogeneity. Okay, so what is principle of superposition and homogeneity? So if you want to know, then this is nothing but normally you can add the signals linearly. Suppose there are two input signals, okay, R1T, R2T. So you can just add those two signals in linear homogeneity by a linear homogeneity principle. R1T plus R2T will be equals to C1T plus C2T, or converting to C1T to C2T. Okay, so that is actually the definition of this transfer function and why it is required. The basic requirement is that we can configure mathematical models for any kind of system with the help of this transfer function, and it will give any kind of output value with respect to any kind of input value. So whatever be the signals the system is getting in the forward path or in the reverse path, that is in the feedback path, so all the signals can be measured with the help of this transfer function. Understood? So you should know all the features and advantages of this transfer function. Okay, so here we will be representing our systems. Okay, any system, whatever we have actually studied, the spring mass system. Okay, so only we use the Newton's second law of motion or D'Alembert's principle. So those were nothing but time domain equations, isn't it? So mx double dot plus cx dot plus kx equals to 0. So time dependent, because x double dot is what? D square x by dt square, isn't it? Acceleration. So here in this transfer function we will be using S domain variable, okay, when the initial conditions are 0, as the condition says. Okay, so now we will be applying this transfer function to this open loop and closed loop system. So here it is written transfer function for an open loop system. Okay, so here this is the system. Okay, so here these input signals or reference signals are converting to the output signals. Okay, so directly you can write the transfer functions will be CS divided by RS. Okay, so here I am writing the mathematical model, okay, or I am configuring the mathematical model of the system by S domain equation, S domain variables. You can see earlier I used to write, okay, R of T. Now I am writing R of S because here it is transfer functions. Okay, so transfer function comes, that is why I am writing R of S. So R of S, GS is the what? This is the control unit or control system gain, or this is, you can say, forward path gain or overall gain, okay, of the blocks. You can say block, okay, means this is a system. So CS is the output signal. So capital R, capital C. So this GS is the overall gain, or for an open loop system, you can say that GS is nothing but T of S, transfer function. So C of S divided by R of S. So what is R of S? It is written Laplace transform of input variable. Okay, G of S is what? Overall gain of blocks, or overall gain of overall gain of the system. Okay, G of S, this divided by this. So C of S, the Laplace transform of output variables. Okay, so till now, if you have any doubt, you can ask. I'm giving 1 minute. Okay, I assume that all of you have understood. Okay, so what will be the transfer functions then for closed loop system? So basically, these closed loop control systems are of two types. Okay, one is a negative feedback system, one is a positive feedback system. Okay, what is negative feedback system? So if in the output, okay, so if the suppose you have given 20 degree as the reference unit or input signal, okay, and you are getting what? 18 degree. So how much actually you need to add to the system again, to the comparator? So it is plus 2 degree, isn't it? So this will be what? So this will be a positive feedback system. So if you are getting 25 degree instead of 20 degrees, so you need to subtract, okay, minus 5 degree in the controller, isn't it? So the sensors will be giving the signals back to the controller. So minus 5 will be subtracted and it will be a negative feedback signal. Understood? So here the first one is a negative feedback signal. So it has one block. So let's say this is the forward path gain. Z of S is forward path gain. R of S is what? R of S is the input signal which is given to the controller. So this controller is represented. You can see there are 4 chambers of this controller. Two, you can say these two are the lines. Okay, crossing lines you can draw in one circle. Okay, so here it is positive signal, it is getting plus 20 degree, you can say. Okay, so here you can see one negative. Okay, so here this comparator will be having four chambers, okay, or quadrants. So where it will be measuring the signals with respect to the positivity or negativity. So here it is positive, so it will be taking as positive signal. Okay, so it will be giving back the error signal, capital E of S, because in transfer function, when you will be configuring the mathematical modeling of any system, so you need to write by capital letters. Okay, so R of S, so positive R of S will be fed. Okay, and this comparator will be comparing with this output signal. So E of S, error signals, will be given to the forward path gain, okay, or overall gain, that is Z of S. Okay, just like the open system, and you will be getting C of S. Okay, and if C of S is not accurate, okay, if there is a lack of accuracy, so the feedback gain H of S is what? This is the feedback system gain. Okay, so H of S, this system will be giving some feedback, that is signal is B of S. Okay, because small bt was the feedback signal which was fed to the comparator. So B of S, capital B of S, will be the signals which will be given, okay, as negative feedback. That is why it is called as negative feedback system, and the comparator will be measuring this negative feedback, and again it will be giving the signals back to the system, okay, processing unit, and finally it will be adjusting, and finally it will be giving the exact or accurate output. Okay, so here it is the block diagram representation of negative feedback system. Okay, and whatever things written below, it is a different thing. Okay, so just you remember that this is not linked with this negative feedback system. This is linked with another thing I will tell you later. Okay, so it was in the next page actually, that is why one arrow mark was there. Okay, so from the bottom of the next page actually I draw this line. Okay, so this is for the second part actually, what actually I am going to teach you. Okay, so just exclude this one with the negative feedback system. Now I will be showing you the positive feedback signal. So here it is written that G of S is what? Overall gain of the blocks in the forward path in each and every system, open, whether it is open loop or closed loop. So there will be one forward path gain. Okay, so this was the forward path, and here it is the reverse path or backward path. So in open loop also there was one forward path gain. So G of S is the forward path gain. You need to remember these terms. Okay, G of S is the forward path gain in the forward path. So B of S is the feedback gain. I told you B of S is the feedback gain. E of S, earlier it was E of T, small e of T, now it is capital E of S, that is error. Okay, so error signal. H of S is the overall gain of all blocks in the feedback loop. Okay, in the feedback part you can see H of S is the feedback gain. Okay, and here it is overall gain, here it is feedback gain in the feedback part, and B of S is the feedback signal. Okay, so these are signals which are on the arrow mark. Okay, this R of S is the signal, E of S is the error signal, C of S is the output signal, G of is the overall forward path gain. Okay, H of S is the overall backward path gain or feedback path loop gain. Okay, so these are not the signals, these are gains. Okay, and here these are the signals. Okay, so our objective is to reduce the control system to a single block by determining the closed loop transfer function for negative functions. Okay, so here this is a negative feedback system. The positive feedback system will be, it will be only positive. So here I have actually mark another circle, so don't do it. Okay, only you need to make 4 chambers. Here it is positive, here it is negative only. Okay, so for positive feedback system, so you need to draw it. Here it is not there, actually I forgot to include that part. So here it is positive, and here also it will be positive. Okay, for positive feedback system. Understood? So this signal, feedback signal, will be positive for positive feedback signal, because I have divided this feedback system of a closed loop feedback system to negative feedback system and positive feedback system. Okay, now what we'll be doing, so you can see there is little bit complexity. Okay, because we have seen in that difference of this open loop and closed loop, that closed loops are a little bit complex. Okay, in configuration, here also you can see some complex structure. Okay, so if we can somehow merge this GS and HS into a simple system, so it will be more simpler. Okay, now we are going to actually do that thing only by the help of this transfer function. Okay, so I think now you can remember what are these Z of S, B of S, E of S, H of S. So here actually that merging of this B of S and H of S, it is mentioned how to do it. We will be doing it by this process. Okay, so from the block diagram, I will not show you this again and again. Just you need to remember that this is R of S, this is E of S, this is C of S signals, and this is B of S in the feedback signal. Okay, and these are the, just wait, yeah, so these are the gains. Z of S is the forward path gain, and H of H is the reverse path gain. Okay, or feedback path gain. Okay, so what is feedback signal then? What is B of S? So B of S is the feedback signal. So how it will be measured? So output multiplied by the feedback path gain. So whatever path gain, okay, that is H of S, whatever be the feedback path gain, when it is multiplied with the output. Okay, means if output temperature is 18 degree, okay, with respect to the input temperature of 20 degree, so that 18 degree will be multiplied by this feedback path gain. Okay, so feedback path gain and the forward path gain will be given for any kind of system. So we need to find out this B of S, feedback signal. So what is feedback signal then? B of S will be C of S, because output is what? Signal. So C of S. So feedback path gain was what? H of S. Okay, because I told you that this B of S will be multiplication of this C of S multiplied by this feedback path gain H of S. This multiplied by this, you will get B of S. Okay, now what is error signal? So how error is measured actually? So input signal minus feedback signal, isn't it? So this is for what? Negative. Okay, So negative feedback signal. That is why, so you need to subtract this RS, because input will be higher than the output. Okay, so whatever be the input signal minus whatever be the feedback signal. Okay, so B of S will give you the error signal. Okay, so input signal minus feedback signal. Okay, don't write feedback path gain. This is feedback signal, so R of S minus B of S. So here in this comparator, if you subtract R of S, because this will be higher 20 degree, you are getting 18 degree. So 20 degree minus 18 degree, what you will get? So you will be getting 2 degree, isn't it? So that will be your error signal. Now E of S is what? R of S, and B of S is what? CS into H of S. So CS into HS I have written. Okay, so mark it 1, mark it 2. Okay, now what is output signal? What is C of S? So error signal multiplied by forward path gain. So what is C of S? C of S will be error signal multiplied by Z of S. Just like B of S is what? This multiplied by this. So C of S is what? This multiplied by this. Okay, E of S multiplied by Z of S. Understood? So yes, multiplied by 0. What is E of S? E of S is RS minus CS HS. We have already found this one. Okay, in the second equation. And what is Z of S? Z of S is, yes, Z of S is Z of S. Here it is written same. Okay, Z of S is forward path gain. So you multiply this with this one, this with this one. Okay, so after rearranging, what you will get? CS. So this will be positive, CS, HS, GS, and this will be RS, GS on the right hand side. Now CS make common 1 plus GS, HS, okay, equals to RS, GS. Now you just take this ratio, CS by RS will be equal to GS will be there, so 1 plus CS HS. Okay, so this will come down and this will be in the denominator, okay, in the left hand side. So what is CS RS? So this is nothing but the transfer function, okay, for a negative closed loop control system, because it is the ratio between the Laplace transform of input variables to the Laplace transform of, Laplace transform of output variables to the Laplace transform of input variables when initial conditions are 0. There is no t. Okay, so we are assuming that the initial conditions are 0. So this is transfer function. So transfer function T of S is equals to what? C of S by R of S, and that means what? G of S by 1 plus GS HS. Okay, so now how this T of S will simplify the system. Earlier what was our system? So this was our system. Okay, this was our normal, okay, negative feedback system or closed loop system. Now we will be modifying that same block diagram. You can see R of S. So directly I am writing Z of S, this transfer function 1 plus GS HS, because I told you that I will be merging this Z of S with H of S. This GS is forward path gain, HS is feedback path gain, okay, or in the this one feedback path gain or backward path gain. Okay, so for negative closed loop feedback system, you can see here in the denominator there is positive. Okay, so this is input, this is forward path gain, you can say this is the reduced form of negative feedback control system actually, and this is what? Output. Okay, so this complex drawing can be converted to a simple drawing, okay, or a schematic representation or a block diagram with the help of this transfer function. So what is the transfer function for this negative feedback signal or a negative feedback control system? So Z of S divided by 1 plus GS HS is the negative feedback transfer function. Okay, and for positive feedback this one closed loop, so it will be negative. Okay, so that is a homework for you. So you just find out this value, okay, only in the error signal, so it will be little bit difficult different, okay, because BS may be higher than this RS, okay, for this positive signal. Okay, so directly I am writing for this positive feedback signal. Oh yes, so one line was written, I told you that it was written here. So here you can see There, hence the output for that simplified actually diagram. So C of S, this is output, will be equals to closed loop transfer function. So T of S into R of S. Okay. So this whole system, this whole intermediate part is converted to T of S, just like GS for open loop system. So TS into CS. Okay, so this RS into TS will give you C of S. That is why it is written as C of S will be what? This multiplied by this. Okay, so T of S, now it is converted to T of S. Okay, so that part it is written actually. So that is why that arrow mark is given from that other page, and that other page is nothing but this one. Okay, so here this line was there, so that arrow mark was continued from this line. Okay, so for positive feedback system, so this is the transfer function. So C of S divided by R of S, here it is negative, so directly I am writing. So here it is the normal drawing for this positive feedback signal. So here it is positive, here it is positive. Okay, so R of S, E of S, Z of S, C of S, and this one feedback gain for this whole system, and B of S is the feedback signal. Understood? So this is a positive feedback signal. So till now actually what we have studied, so first we have seen the classification of this control system. So control systems are basically divided into two categories. One is the open loop control system, another is the closed loop control system. So I told you that in open loop control system there is no control at the output. Okay, whatever the system will be given as an output, so you cannot, the system will not adjust itself. You need to adjust the system manually. Okay, so in open loop control system, in closed loop control system there will be a feedback loop. So the feedback loop will be adjusting. Okay, it will be giving the signal back to the comparator. Okay, and it will try to adjust the system. Okay, and finally it will be giving out the output as desired. So that is a closed loop control system. Then this closed loop control system can be divided on the basis of this feedback system as positive closed loop control system or feedback system, or negative feedback closed loop control system. Okay, so we have seen this system, and with the help of this transfer function, so we have actually transformed those block diagrams. Okay, and finally we have got the representation of those block diagrams, or you can say the schematic drawings of these systems. Okay, feedback systems. So I told you that I forgot to mention, but here it is. Okay, this one, this is positive feedback system. Okay, so it is already there in the notes, okay, or in the PDF file. So I will be sharing this one with you in the Google Classroom. Now you can take one problem, a negative feedback system with a forward gain of 2. Okay, negative feedback system, forward gain of 2 and a feedback gain of 8. So if it is a forward path gain, so what is the value of this, for actually what is the representation of this forward path gain? It is Z of S. Okay, it is 2, and feedback path gain is what? H of S. It is 8, is subjected to an input of 5 volt. So what is the input? So input is nothing but what is the input? Input is R of S. So R of S is 5 volt. So determine the output voltage of the system. Okay, means C of S you need to find out. So here it is, C of S will be what? Transfer function into input signal, isn't it? Because I told you this one, that arrowhead was given. Okay, so from this you can see this R of S will be RS multiplied by TS. This is TS, GS divided by 1 plus GS HS. This is TS, will be equals to C of S. Okay, so input signal multiplied by this transfer function gain or forward path gain will be equals to the output signal. Understood? So with the help of this you can find out the answer. So GS is given as 2, feedback HS is given as 8. This formula is there. So GS HS you can put the value of this one, forward path and feedback path gain, and the CS RS is given as what? 5 volt. Okay, so you can find out CS, okay, output signal in S domain. Okay, so it will be multiplied by this RS, so you will be getting 0.5882 volt as the output unit. Understood? So that is why it is very much important to find out the transfer function for any kind of system. Okay, so it will give you directly the forward path gain. or simplify the system. Okay, so I think till now all of you are actually getting the things what actually I want to make you understand. Just a small thing it is left. Yeah, so mathematical modeling, I told you basically that for analysis and design of a system, a mathematical model is necessary. Okay, and it describes the behavior actually of the system, isn't it? And that the process of obtaining the mathematical description of a system is known as the modeling. Okay, so there are actually one algorithm, okay, how to construct the mathematical modeling for a system. So I will not go to the detail, okay, of this. Just you need to remember, because sometimes it may ask, okay, it can be asked in the examination. That is why it is important to commit to your memory all the steps. Very simple, okay, very simple thing. First, you identify the system variable. System variable means what? Whatever input signals, okay, or output signals, those will be there. You need to identify those one. So start, because we normally write algorithm in this way. Okay, so there is a start. So after that we will be finding out the system variable. So write the time domain equation by system variable time domain equation. Okay, so those equations are nothing but our Newton's second law equation, or for electrical system it is Kirchhoff's law equation we need to write, because those are time domain equation. Okay, but we need to convert this time domain equation to what? Laplace transform. Okay, so these time domain equations can be converted, okay, or these parameters can be converted to Laplace transform, isn't it? Because all of you have studied in mathematics. So these are actually applications of this Laplace transformation, why you actually studied Laplace transform in your mathematics tree. Okay, that is why it is very much important, okay, to study this transformation part. Okay, so take Laplace transform of this time domain, these one parameters or variables with the initial conditions as 0, because we need to very much careful about this one. Okay, so when you are converting the time domain parameters to Laplace parameters, okay, so initial condition should be 0, otherwise you cannot find out the transfer function. Okay, so identify the new input and output variable. Now you need to identify those input and output variable with respect to this Laplace transform S, okay, in domain S. So by elimination method, so some methods are there by elimination method. This one actually it is not distinct. Okay, just identify the input and output variables. So by elimination method, represent the resultant equation in terms of input and output variables. Okay, so some equations will be there, so it will be a resultant equation. Okay, so that resultant equation can be represented by this input and output variables. So I am having actually here are some of the examples. So you can see I will be able to show you. Okay, but I will not go to the details, but I will be able to show you those things. Okay, so lastly, so you need to this one, obtain the transfer function by taking the ratio of the Laplace transform output variable to the Laplace transform of the input variable. Okay, because transfer function actually we need to find out finally to configure any mathematical model for any system. Okay, so after getting the transfer function, all the things will be easily obtainable. Okay, so finally we will stop, and this is also called a flow chart for deriving the transfer function actually. So you can say that this is a basic procedure of configuring any mathematical modeling for any kind of system, or to find out the transfer function. So basically this is the step, okay, or the algorithm you can say. Okay, so up to this much, okay, you need to study for your module 4 for exam purpose. Okay, and in your syllabus there are some of the this thing introductory part of some of the this one control system. Okay, PF controller, okay, PID controller, all those things are there. So if you just want, you can do a self study. Okay, for those things introductory part, because those systems are completely electrical systems. Okay, so I don't have also that much of depth knowledge of those electrical systems. Okay, but if you want to know the introductory part, you can okay, see in the net also. Some YouTube videos may be there for those controller, but you will get some idea actually. Okay, so in higher studies, in when you will be studying nonlinear vibrations, so it may help. Okay, but uh, I think up to this much, if you know, then also it is sufficient for you. Okay, so one part actually it was important, but I think as this is not important for the exam purpose, that is why I am not teaching you this thing. Okay, very small part, that is mathematical modeling part. Okay, because already we have done it manually. Okay, for all kind of systems, isn't it? All for all kind of systems from the very beginning of mechanical vibration. So we have done it manually by applying Newton's second law of motion or Kirchhoff's law. Okay, in any system, linear system or non this one, the translatory vibration, or this one, torsional vibration. Okay, so I will not go to that part actually, otherwise it will be little bit confusing for you too. Okay, but if you want, okay, some of you may want that, sir, please teach us this thing also. So I will be taking extra session if it is necessary. Okay, but you need to inform me, that is the thing. Okay, but for exam purpose, up to this much it is sufficient for you. Okay, up to this transfer function. So how to apply this transfer function and how to get the mathematical modeling, so in the later part actually I have elaborated. So if you need extra class for this, okay, so you need to inform me, so I will take the class after this. You can say tomorrow I will not take your class because you have exam, isn't it? This one lab exam also, so you can prepare as well. So after 15th I will be taking a class if it is necessary. Okay, but you need to inform. So this part I will be teaching you. Okay, if necessary. So
Yes,
these are
sir.
the
Okay.
mathematical modeling. Don't go. Okay, just wait. Just be there. Okay, all of you, please. Okay, so this is the actually Kramer's rule. You have studied, okay, to solve the linear equation, two types of linear equation, how to solve, all those kind of things are there. So we need to apply this mathematics and Laplace transform to solve the this one, systems, mechanical systems. So up to this much it is there, and I will be sharing this note, okay, notes with you also. Okay, so any problem in understanding anything up to this transfer function, this algorithm? Anything you want to ask?
From my side, no problem, sir. I don't know
Okay.
others.
Sivanus, Bhargav. Okay, so don't go, just wait. I will be taking your attendance too before concluding. Actually, yes, because this may be our last class. Okay, so first of all, yeah, I want to actually say you something about class test 2. Okay, so class test 2, I have checked your answer scripts. I have actually I have the marks with me. So I will be sharing your marks. Okay, in the WhatsApp group. So will it be okay to share in the WhatsApp group, or should I show you now in my screen?
So it will be okay to share.
Okay, in WhatsApp group now. Okay, so I'll
Yes, yes,
be
sir.
sharing it shortly after this class. Then regarding the lab exam, I think all of you are aware about the lab exam. So it is of 20 marks. It will be of 20 marks. So the syllabus for this lab exam, I have told you that from the very beginning, module 1 to module 3 up to force vibration. Okay, so you need to study the basic things. Okay, so just like the small, okay, means things just like you attempted in the class test second. Okay, so those type of questions will be there. So maybe there will be 10 questions of 2 marks. Okay, so 1 hour will be given. So you need to write down the solutions. If you are asked to solve, then you need to show the solutions. Don't write the answer directly. If the answer is, let's say, 54.56 radian per second, so you need to show the formula also. Okay, for if it is natural frequency, so omega n equals to under root k by m. So just like that, you need to write it very carefully. Okay, as because this is 20 marks exam, so it will be your final viva come written exam. Okay, for your lab exam. Okay, so because some exams will be of theory based exams, will also be means questions will also be there, 2-3 questions will also be there. So I will be taking it as a written exam plus Viva exam. Okay, so that is why for that 1 hour, so you should be very much careful, okay, in answering. Okay, and you write your name, whatever it is, the details will be there, just like your class test 2 you have done. So you need to write your college ID, you need to write your name. Okay, so all those things should be written clearly, and you need to this one answer very distinctly, okay, with a very clear handwriting. Okay, so regarding the lab file, so till now actually we have completed around 6 practicals. Okay, so there are actually 8 experiments. So what actually I will be doing, one this one, just wait, okay, I need to check something, just wait.